now we want to study about connectivity and cycles. First, we want to talk about connectivity. So before we define connected graph are the graphs where we can find the path between any two vertices in the graph. And those are the connected graph. And intuitively, if you have more edges, then it tends to be more connected. And then if you have less edges, it tends to be less connected, which is not always true, but on an intuitive level, that's the correlation. So probably having less edges, the graphs are more simple. The graph has more simple structure. So we study about the minimally connected graph, which were 3. As any graph are disjoint union of connected graph, studying connected graph is sufficient. And then among the connected graph, the one with the most simple structure was the minimally connected one, which is 3. So now we want to study about more connected graphs than 3. So what are the graphs which is more connected than 3, but hopefully not too connected, not too complicated, so that we can understand. So in order to talk about this more connected graph, we need to, define how we will measure this connectivity. So we didn't really define what it means to be more connected. So we want to define them. So again, as before in studying trees, we were talking about cut vertex and cut edge, which was about separation. Once it's separated, there are no paths between two vertices. So somehow connection, which is the existence of paths between two vertices, are closely related to the separation. So that was like opposite concept. Once you separate, then they are no longer connected. Once it is connected, they are not separated. So we define, so it's very natural to define separation in order to understand the connectivity. So a separating set or we also call it a vertex cut of graph G is a set S, the vertex set S such that G minus S has more than one component. So there is a bit difference between cut vertex, how we define cut vertex, and then cut edge, and how we are defining the separating set and vertex cut. For example, when we are defining a cut vertex or cut edge, we care about the increment of the number of components. So if your graph is connected like this, so this was a cut edge, because once you delete it, then it separates, it increases the number of components. And let's say this is your graph. And then once you delete this, you have more component than before. So this was cut vertex. But here, how we define this is having more than one component. So from this definition, even this is a separating set, or this is a separating set. Once you delete these 3, you still have more than one component. So more than that, even empty set is a separating set in this graph. Okay, and we say that our graph is K-connected if it has two conditions. It has more than K vertices and every separating set has size at least K. And we define the connectivity for G, which we write as a kappa of G, is the maximum K such that is K connected. So this is how we define K connectedness. And now we see why we have this definition instead of an increment of number of components. Because we want the connectivity of this to be 0. Because this is not connected. This is disconnected graph. So that means empty set is a separating set here. So in this graph, what's the K which satisfies this? Every separating set has size at least K. So it has size at least 0. So this is 0 connected. So its connectivity of this graph is 0. That's why we define it this way. There is an additional catch. So you understand why we define it this way. Because if this is higher, then it means it is difficult to separate the graph. That means it is highly connected. But what about it? It has more than K vertices. The reason why we define it this way is that in terms of considering the connectivity of complete graph, this additional condition on this definition becomes very natural. So what's the connectivity of complete graph? For one, it doesn't have any separating set. You have, say, this K5. No matter what vertex you delete, no matter how many vertices you delete, you always end up with one component or 0 component. It's never become 2 components. So if we just write this part, then the connectivity of complete graph becomes infinity. But we don't want that. We want we will see many good properties of this connectivity. And we want this parameter to be natural parameter. For example, one of the things that we want is that the deletion of one edge or one vertex does not change the connectivity much. Deletion of one vertex or deletion of one edge or addition of one vertex or addition of one edge. We want those additional deletion will change the connectivity by almost 1. It is very natural because whenever you delete one vertex, how does the separating set size change it? Deleting S from the remaining graph is same as deleting S together with this one vertex from the original graph. So if you think about it, this deletion or addition on one vertex does not change the connectivity by more than 1. Also, it's not difficult to see that the deletion of edge, it also does not change this definite part by more than 1. So in terms of that, so this has connectivity 3. So we want this complete graph. If this has connectivity infinity, then this gap says that we cannot say deletion or addition of one vertex changes the connectivity by almost 1. It becomes false. So we add this part. So this has actually connectivity K5 is actually 4. Because what? It has more than 4 vertices, right? But it doesn't have more than 5 vertices. So 4 is the maximum number which satisfies it. So the connectivity of complete graph is n-1. And in order to achieve this, we add this one more condition in the definition. Okay. And we also define edge connectivity. And in terms of vertex connectivity, this separating set, multiple edges means nothing. We are deleting vertices. And then we care about whether the remaining thing is corrected. In terms of that, having 2 edges or 1 edge does not make any difference. But in terms of edge connectivity, we will talk about edge deletion. In terms of edge deletion, the multiple edges make changes. So we define for multigraph to be edge connected. If deleting fewer than k edges is the connected graph. Then we say this is k edge connected. And we define the edge connectivity. And we write kappa prime of G. So you see the pattern. Whenever we have certain parameter, we add a prime, that it becomes edge parameter instead of the vertex parameter. This is what? Maximum K, such that G is K edge connected. And we define one notation for vertex that's S and T. We write bracket S and T for the set of edges from S to T. And on edge cut, we define this name is the set of the form S and S complement, where S is a non-empty set. So this is natural when we talk about edge deletion. How many edges do we have to delete to connect the graph? And this edge cut is between the two vertexes, S and its complement, and the set of edges between. And in terms of studying edge connectivity, this edge cut is an important concept, because essentially when we want to disconnect the graph, the only sets we have to consider are edge cut. So if you have a graph with n vertices and m edges, the m is, let's say m is some constant times n square. Then in order to check its connectivity, we have to consider all possible edge deletions, which leaves a disconnected graph. Then, if you just try not to be smart, then there are 2 to the m, which is 2 to the c times n square possible choices of edge set to consider. But if we just know that we only have to consider the edge cut and 2 to the n choices of edge cut. So in this case, this number is much smaller than this. And if your graph is not disconnected, then we know that m is always at least n minus 1. So this number is, even if this is not quadratic in n, this number is always much bigger than this. So edge cut provides a more restricted possible choices of consideration in terms of edge connectivity. In fact, the following proposition actually confirms it. So every minimally disconnecting set of edges is an edge cut. Meaning that if you have a graph, and then somehow there is a set of edges which disconnect the graph, then such an edge set is minimal in terms of this disconnecting one, meaning that there are no, this deletion leaves these two components, and somehow, without this red edges, these three already disconnected, so this 4 was not minimal. So if we just take the minimal one, this is always an edge cut. And proof is simple. If say you have a edge set f such that g minus f is disconnected, then what? We let S be the vertex set over, you choose a component and then you take the S to be the vertex set of such component. Then what? The edge cut F between S and S complement is contained in F. So you have this F, so that after deleting it, it's like disconnected, and then you choose one component. Then this component is a component after deleting F, meaning that all the edges between this component and outside belong to F. So this shows that every disconnecting set contains an edge cut. So if your disconnecting set is minimal, then it must be an edge cut, because edge cut itself is also disconnecting set of edge. Okay, so we define this connectivity, edge connectivity. In order to better understand it, we want to explore the relation between this new parameter and some other parameter that we know. So first parameter that we want to consider and then see the relation is the minimum degree. Because so here what? Deletion of vertices and deletion of edges, and then we want to see how those operations disconnect the graph. And what's one of the easiest way and most simplest way to disconnect the graph is an isolating a vertex. If you have a vertex, then you might delete all the edges inside with it, and this becomes a component itself. So you disconnect everything else from this one vertex. That's one way. And instead of deleting edges, you could delete all the neighbors of this vertex, again isolating this vertex. This vertex becomes an isolated vertex after deleting this edge. And when doing this, you could choose the vertex with the minimum degree. Then the number of edges or vertices you have to delete becomes same as the minimum degree. That provides the following relation. This logic shows that there are relation between this connectivity, edge connectivity, and minimum degree. And Whitney in 32 proved that the connectivity is at most edge connectivity, and edge connectivity is at most minimum degree of G. So, as I mentioned, if we delete the edges incident to a vertex, deleting the edges incident to a vertex disconnects let's say vertex of minimum degree. So edge connectivity is at most the minimum degree. And then now what we have to prove? We only have to prove that the vertex connectivity is at most edge connectivity. So in order to prove this, we take a smallest edge cut. S bracket S and S complement of size say K prime, which is kappa prime of G, the edge connectivity of G. So you have this S and then the complement of S. So there will be some edges between them. And what do we have to show? If it has 1, 2, 3, 4 edges, then we can delete at most 4 edges to disconnect it. That's what we want to show. What can we do? In this case, in this specific picture, either you delete these 3 or you delete these 3, depending on whether there are additional vertices here and here. If there are only 3 vertices here, then deleting all of this doesn't do anything. We want to isolate some vertices. We want to disconnect some vertices here. So the most natural thing to do is delete these vertices so that these edges are also gone when you delete the vertices. So in order to do that, I mean, as I mentioned, we need to make sure that some vertex here and some vertex here are left not deleted so that they are disconnected. And how do we do it? If there exists X in S and then Y in the complement, such that XY is not in the graph G, then what? For each edge E in this edge cut, we know that it has an endpoint, not X or not Y. This is X, this is Y. And for this edge, this vertex is not X and not Y. For this edge, this vertex is not X and not Y. For this edge, this vertex. For this edge, I mean either one. So what we do, we add such an endpoint to T. Now, what we have that this T has size at most K prime, which is same as the number of edges in this edge. And what? X, Y are not deleted when we delete T. X, Y are not in T by the definition of our T, and this lie in different component of G minus T. And once you delete T, all the edges in this edge cut are gone, so it's disconnected. So, what? This vertex separating set is at most has side K prime. That's what we want to prove. We want to show that every vertex cut has side at most this, but we assume that the existence of such an X and Y. What if not? Otherwise, what? All vertices of S are adjacent to all vertices of S prime, S complement, then what? K prime is same as the edges between them. Okay, it could be multigraph, so it's at least size of S times size of complement. But what do we know this? This is two number, which is at least 1 and at most n minus 1, and which sums to n. So its multiplication is at least n minus 1. And the vertex connectivity of G is by definition at most n minus 1. So in this case, we have this, and then the other case, we also have this. So this proves that the vertex connectivity is at most edge connectivity. Okay, and now we have defined this connectivity, edge connectivity, and then we see the relation between this and minimum degree. And what's our goal? We want to understand the structure of K connectivity graph. And how do we do it? Before we study about tree, and then how did we understand the structure of tree? We proved that there are some operations which generates all tree. Namely, we show that we have tree, and then we can add one leaf, and add another leaf, and add another leaf. And by doing this, we can create all the trees. Also, this is one. Another one was that we put all the isolated vertices, we add edge. While not creating any cycle, we add an edge. Yeah. We keep add an edge without creating any cycle. Then we obtain trees. All trees can be obtained this way. And then this provides an understanding of its structure. In some way, this tree can be built recursively, so that if we want to test certain property, then we apply induction, and then this recursive structure provides a way to prove the property. And also intuitively, say this addition of keep adding leaf already give us some understanding of its structure. So again, we wish to understand the K-connected graph via some operation that creates all K-connected graph. So if possible, we want to do this. If we find some operation which creates all possible K-connected graph, then that would be very good for us. I mean, in fact, if moreover it's preserving the K connectivity. Here, you take a tree and then you add a leaf, then it is again tree, you add a leaf, it is again tree, again tree, again tree. But like this, here, it could be 4x at some moment. But in this operation preserves of being tree. So that's, I mean, intuitively more understandable. I mean, it provides more understanding on the structure. So we want to consider such operation, which will create all K-connected graph and then also preserve the K-connectivity. In fact, I mean, we will consider the following vertex K-split. So this operation called vertex K-split forms what does it do? It forms a graph H from graph G by what? We replace one vertex X in G with what? Two adjacent vertices, X1 and X2, such that in the new graph, the neighborhood of X1 and neighborhood of X2, if you take the union, it's exactly the neighborhood of X in G and X1 and X2. And moreover, each of Xi has at least K neighbors in H. So for example, if you have this graph, and we take this. What we do, what we do is we separate this one vertex into two. So you keep the outside vertices. And what we do is we take this and then this is X, and then you take it into X1 and X2, and then they are adjacent. And then previously this has 4 neighbors, and then we want to kind of we want to distribute these 4 neighbors to neighbors of X1 and X2. For example, you can make it adjacent to these 3, then X2 to adjacent to these 3. Then this is a vertex 3 split. As well as vertex 2 split and vertex 1 split, but not vertex 4 split. Sorry, it is actually a vertex 4 split. Yeah, I said it wrong. I counted it wrong. So every vertex now has degree 4 and degree 4. So this is vertex 4 split. And then if we delete one of these, and this is what? Vertex 3 split. And we can prove that this operation preserves the K connectedness. So for graphs, H is obtained from K-connected graph G by vertex K split. Then H is also K-connected. And how do we prove? Again, in order to prove this K connectiveness, we consider its separating the vertex cut. So we consider K split with x1 and x2 replacing x. And let S be a vertex cut of H. And there are several cases. If x1 and x2 are all contained in this S, then what? Then S, you delete x1 and x2 and add x. So what? You have S and x1 and x2, and deleting S leaves a disconnected graph. Then in the original graph, G, this is at H, this is G, you can again consider S with at the point of, with x1 and x2 replaced with x. And this set is a vertex cut of G as what? A vertex cut of G has size at least k, so S has size at least k plus 1. So this has size at least k, meaning S has size at least k plus 1. Also, if what? H minus S has x1 or x2 or x1 and or x2, the H x1, x2 as a component, then what? If you have S and then here x1 is there, then what? Then all of the neighbor of this vertex has to be in S, not in somewhere else. Then S contains either neighbor of x1 or neighbor of x2 or neighbor of x in G. In each case, S has size at least k, because it's vertex k split, meaning that the abstract split x1 and x2 both have a degree at least k. But the remaining case otherwise, and let's say S intersection with x1 and x2 is empty. Let's do one by one. If this one is 1, say x1 is in S and x2 is not in S, then what? S, you have x1 and x2. x2 is not a component itself, but there are other vertices here as well. Then what? S minus x1 union with x again. So this is in H, and in G, what? S, you have X, this is Y, and Y still is here, and then there are other components here as well. This is a vertex cut in G. S, again, S has size at least k, and what? The last case is that this is 0. Then what? Again, S has here. There is one component which contain both x1 and x2, because x1 and x2 are adjacent. And then, because this is not the only component, I mean that these two vertices are not component itself, there are other vertex y here as well. And there is another vertex, another component here as well. Again, this corresponds to this picture. So, S union with, no, S itself is so in G, what? You have S, then Y, X here as well, and then other component. So this is again vertex of G. So in any case, it's vertex called aside at least K. And also, I mean, once you apply the K split, then H has at least K plus 1 vertices. That's for sure. That's automatic. So this proves that H is a K connected graph. So indeed, this K split is an operation that preserves the K connectivity. And using this, we will study the structure about 2 connected graph and 3 connected graph. And that's what we will do in next video. In next video, we will study the structure of 2 connected graph.